Okay, so now we're ready for something super cool. So let's think back to the problems on their opener. And if you have this way to describe the terms in a sequence, and you're finding some term, so this would be the index, we put in 1,000,000, but it's some super, super, super big number. Is it true that that outputs 0? It's actually not true because it's some number that's super close to 0. And in fact, the bigger you make the index, the closer this output gets to be 0. Okay? And so this isn't really a true statement, but it is an idea we want to really say. Like the bigger you make that power, the closer that number is going to get to 0. And the same thing here. If you have this exponential relationship, the bigger you make the power, or your book introduces it when we're talking about sequences. So the larger the index, the further out in the sequence you get, the larger and larger and larger that number is going to get to be 0, to infinity, like ginormous. Okay. And so what people did, mathematicians did, is they wanted to describe this idea, but it's not true to say that this output is equal to this number. In fact, this isn't even a number, that's an idea. And this output is never equal to this number. So how did they want to describe the idea? They came out with this idea about limits. And so here's the notation, and then we'll go back and we'll write the notation under the statement. So this LIM, this stands for limit. And so in 2 algebra, in pre-calc before this point, we always really talked about the output of a function. So we had some function, and we put in a number, and we talked about what the output actually was. Limits talk about what you expect the output to be. Sometimes that's equal to what the limit actually is. Like the expected output is the output, but not always. Okay, so this symbol is limit. Okay, and in here goes the function rule, the rule for generating something. Maybe it's x, maybe we're going to use n because we were using n when we got to sequences. We'll move it to x in a little bit. Okay, so this right here is the rule. What's the rule you're looking at? Okay, and then you need a little template for what's the name of the variable. Okay, and then you want to say, where are you looking to send the variable's input? What do you want the input to be? And in our case, since we're getting further and further and further along in the sequence, we're looking at really the end of the sequence. We want the input number to be essentially infinity. And then this is telling you what the expected output is. Okay, so we're going to use that template. And we're going to go back here. And we are going to write this idea, excuse me, the way that mathematicians write it. Okay, so we are taking this rule, so that's like our function, and our variable is n, and we're saying what's happening to this as we make the n's be infinitely big. And so we can't actually get an output there of 0, but we know that the bigger we make the n, the closer n gets to be infinitely big, the closer the output will be to 0. So this is how we say that idea. Okay, let's do the same thing for the next one. Okay, so our rule is we're taking 1/2 times 1.03, and we're going to use n to be the variable because we're thinking about sequences and n's a natural number. Okay, and we want to think about how these outputs are looking, how are they behaving, what happens. So we're not actually thinking about an actual output necessarily, but what happens if we make the inputs be really, really big. Okay, and we saw, oh, well, this is going to get ginormous, and so this is going to be some number that's infinitely big.